Okay. Okay, it's 8:45. Good morning, students. Today, Wednesday, 2nd of June, it's lecture number 12, and it's the last lecture in the series on multibody dynamics. This lecture is actually the final climax of the whole course, because in this lecture, as an example, I'm going to look at a complex 3D multibody dynamic system and how to derive the equations of motion for that. And we can do that because in all the previous lectures we learned all kind of tools. Of course, the most famous tool, best tool for an engineer is scissors. But on top of that, we learned all kinds of tools: virtual power, Newton-Euler equations, constraints, all kinds of methods, numerical integration. Our toolkit is full, and with this toolkit we now can derive equations of motion of this system. Okay, since all the theory is there, I'll just do an example to show you how it works. Okay, and the example, by the way, is also closely connected to the homework problem. By the way, for those who are watching, great work on the bonus question, the tinkering with the Euler angles, the apparatus, which I have somewhere here. I'm still in the process of grading those, so relax, that will come. Okay, let's do an example. And as an example, I take the following multibody dynamic system. A little bit room. That is we start with a disc and a pendulum, but in a 3D manner. So we have that's not a nice disc. We have some disc here with some thickness, right? It has a center. Then the disc can rotate, and that is fixed to the ground, right? So there is apparently some inertial system. And we call it an X, Y, and Z. And then this body, of course, which we can give a number, number 1, has of course a body fixed triad, and since the body is mounted here, so this is then the second coordinate system. So you could say that's a small z, a small x, a small y, and a small z. Since the rotation is all about this axis, we call that alpha, right? So this is then, we have to give it a name. Well, let's say this is B1 as a coordinate system. So now this disk can rotate with respect to our inertial system. On top of that, then we mount on the disk in the y direction. We mount a hinge, and that is mounted here, and it has a relative rotation beta, and then of course, and then we in series mount with that hinge another hinge which is in the negative y direction, like this, and we call that rotation gamma. And then on top of that we mount a pendulum. Yeah, and the pendulum was going, no, that's not nice, it's going down like this. Yeah. So that is a nice pendulum. Of course the pendulum has a center of mass here. Oh, by the way, this is of course the center of mass of body 1, right? This is body 2. At the center of mass, a mass and a mass moment of inertia. Everything running, yeah, no problems. Okie dokie. Then let's put some body fixed triad system there. We'll call it B2, and again we can use just X, Y, and Z. Since we have clearly defined, oh, I didn't mean to do that. I discovered a new thing of the 2, B2. Anyway, since we, that's crazy, B2. Since we defined already a coordinate system, B2, then X, Y, and Z, they are clear what we mean by that. We don't have to put all kind of accents and so on. And of course you have to put dimensions there, right? So the disk has a radius, the pendulum, let's do a perspective thing. The pendulum has some length, right? And then you have to define where's the center of mass, probably in the center, in the middle. You have to give some masses and so on. Okay, so what we want for this system, we want to derive equations of motion, such that if there are applied forces, and in our case let's do simple, let's say the applied force is just gravity, but you could also say, no, we apply all kind of other forces there. That's a detail, but for a number of applied forces we want to know what is the motion of the system, and to make a long story short, we have to derive the equations of motion which determine the accelerations of the degrees of freedom. Okay, so a number of words already popped up. So the first thing is equations of motion. Equations of motion. So how do we derive those? And unfortunately, in this course, I gave you a number of tools to do that, right? So, meaning that you have to make a choice. And I think in life there's nothing harder than making choices. And when you're young, that's super easy. You have less responsibility. You have to make not so many choices. But when you get older, you get more options, and then you have to are more often more in a situation where you have to make a choice, and that's difficult. And again, so this is difficult. So what are we going to do? Well, first, as I said, degrees of freedom. So we have to find out how many degrees of freedom does the system have. Now, from your mechanical intuition, you can already think, oh yeah, it should be probably 3 or something like that. That's okay. But actually, I like to not use religion here, but just science, right? So, and the science tells me, oh, I can find the number of degrees of freedom by counting the number of rigid bodies and counting the number of constraints and then subtracting those. Okay, so degrees of freedom. How do we do that? Well, first of all, let's do some counting. So we have 2 rigid bodies, right? That's the disc and this disc and this pendulum. And then how many constraints do we have? Well, we have 3 hinges, right? Hinges or revolute joints. Joints. But there's a snake here because here the revolute joint is connected. Oh man, go back. Here the revolute joint is connected to another joint. And that makes it a bit troublesome. So how are we going to solve that? Actually, if you look at this system here, why is it always... Okay. If you look at the system here, then there is probably a body in between to connect those 2 hinges. So if you want to do some counting, you actually have to think, well, the system is a bit more complex like that than that. So we have a disc, and there's a hinge, and that's connected with the ground, so that's body number 1. Then here we have a hinge which is connected between this body, and then here is like a virtual body. Let's say that's number 3 because we already have a number 2. And then connected to that virtual body is a 3rd hinge, and then here we have body number 2. And now we have simply one body, I did do something wrong here. Anyway, we have one body here, and we have the 2nd body here, and then the 3rd body, intermediate body, and then all the hinges are between the bodies. And now we can do a simple counting, because we can now say we have 3 bodies, meaning we have 3 times 6 degrees of freedom, right? That's 18. And then we have 3 revolute joints. And the revolute joints, well, each joint, you could say how many constraints are there. So the body has to be in place, that's 3 constraints, and then 2 rotations are restricted. That's one way of thinking. The other way around is like saying, okay, it's between 2 rigid bodies and 1 degree of freedom remains. So apparently I have 5 constraints, which complies with 3 constraints to put them in position and 2 constraints to restrict the bending. So it's 3 times 5, meaning 15. Then we subtract, we get the number of degrees of freedom is 3. And that makes of course sense because those 3 are exactly okay, oh, this is better. is exactly this one, and this one, right? Okay, so 3 degrees of freedom. And then we have to make a choice, of course, about what tools we're going to use for deriving our equations of motion. So one way would be, for instance, to do the DAE approach, right? And then we have how many equations do we get? So the number of equations is then, of course, well, we have 18 bodies, so we have 18 equations, differential equations for that motion. 18 differential equations plus, yeah, 15 constraint equations, right? Equations making a total of 20, what is it, 33 equations. So the system is a 33 by 33, right? So that's a big system, but doable, of course, with the same famous structure and with the accelerations here and Lagrange multipliers, and that's doable. However, maybe, and since it's an open loop structure, that's even more easier. Another way would be to say, no, we could do Lagrange, for instance. We use Lagrange, and we use generalized independent coordinates. And then how many degrees of freedom do we then have? Then we talk about the QJs, right? That is, well, in our case, super simple because we have alpha, beta, and gamma here. Those are the degrees of freedom, 3. So then we have here alpha, beta, gamma, only 3. So we get only 3 equations of motion. And compare 3 versus 33. So in one case you have a very large system, and in the other case small. However, the large system is easily built. That's really plug and play, and not like Windows plug and play, but real plug and play. And but in the Lagrange method, that's a long route. I mean, you have to define coordinates in terms of generalized coordinates. You have to find angular speeds. You have to determine kinetic energy, potential energy, maybe other applied forces, transformations. Then you have to differentiate that twice, collect terms. Complex. However, you can automate it, so that's nice also on the other hand. But a more straightforward and also computational far efficient method is using the TMT method. And why do I say computational? Because you can just calculate everything by parts. Like in the finite element method, you can do just element by element and then add that up. And you can also do that in the TMT method. And of course you could also do that in the Lagrange method, but if you have a chain, then the last body still becomes very complex. Anyway, that's not the topic for today. So that's one route, that's the other route, and then TMT method. Okay, and of course, for the TMT method, we again need generalized coordinates, and we're going to take the same, of course. We're going to use these as generalized coordinates. And you would already have guessed, I think, that I'm going to use, well, what shall I use? DAE, Lagrange. Of course, we're going to use TMT methods, right? So we're going to do this one today. And if you want to, I mean, you can also do it the other way and then compare, right? Okay, so let's do TMT approach. So what was the TMT approach? Well, the whole basis of the thing was, of course, virtual power. So we have the virtual power of the system, which is the sum of the virtual power of all the bodies, and B is just the bodies, and in this case it's 1 to 2, right? And then the virtual power of each body is, well, it consists actually of 2 parts, right? It's a virtual power of the Newton part plus the virtual power of the Euler part. And why do I distinguish so clearly between them? Because these equations are sort of separated, right? As we have seen. For the Newton part, you can just shrink the body to, oh, it's a point mass, and then it's x, y, z, and that's it. And for the rotational part, suddenly you have to think about angular velocities, not so much about angles, angular velocities, and torques, and they seem to be disjunct from the coordinates. I say seem to be. Okay, so how does that work then for our complete system? So for our system, it is the sum over the bodies of, and then first the virtual power of Newton. Well, that we know that part, right? That's the applied forces on the bodies, minus the inertia terms, x double dot of the bodies, and then times the virtual power of the bodies. And should I do, oh yeah, I write matrices, so I do transpose. Well, maybe, yeah, that's okay. That's okay for now. Plus, so this is again a sort of mixed mode. For every body I have a vector. For every body I have a vector here. A vector of XYZ forces, XYZ. Yeah. So maybe I should clarify that, what that is. I'll do that in a second. I'll just continue. First, so that is the Newton part. Then we go to the Euler part. And I need a little bit more space there, so I have the torques applied to the body, minus, and then the inertia terms, but the inertia terms are not as simple as they are here, right? They are a bit more complex, because we have mass moment of inertias, right, from that body, times angular accelerations, and then we have these convective terms. So omega the body cross, and then the angular momentum of the body. Close the bracket, and it's virtual power, right? So then we have to do times the virtual power of that body, and then we can close our bracket. So we sum over all the bodies. So we sum to get the Newton part, and then we have the Euler part. You may remember that well, if we do everything in a inertial fixed thing, which we will do here, then that sort of works. If we do that here, then we are in trouble, because then the mass moment of inertia will change all the time. Whereas if we take a body fixed coordinate system, or triads, then it doesn't change. So what we really like to do is actually put everything in a body fixed frame. So for here I'll put a prime there to indicate that everything is in a body fixed frame. Fixed frame. All terms, right? Everything. And of course this is all inertial fixed. Inertial fixed. Well, frame or triad. Or, and that is actually the whole dangerous band here, and I see in my notes that I really wrote dangerous band, so, okay, how do we do that? Zit, watch out, zit, zit. Dangerous band. So this is really a dangerous band, because, and especially this part, because we have to do it in this body fixed coordinate system. Or in other words, if I say what is xb, that is x, y, z of body b, at the cm of course, at the com. But it is actually what we're going to do, we're going to do the xb expressed in the end. That is what we're going to do. And what is the omega of body B? So that's the omega about x, omega y, omega z, b in in a body fixed triad. So in our case it is, and you don't have to say the omega is at the COM, because when you have a rigid body and it has an angular speed, every part of that body has that same angular speed, right, or angular acceleration. Then we say that's in all the individual body frames. So I should say that's the omega B in this B, and then I need an index for all the different bodies, which I already have, so that's B. So expressed in all these frames. And I don't want to, for now, I don't want to write every time this guy and this guy, so I will stick to the prime and say nothing. Okay. Actually, we're almost done now, because we have our equations here. The only thing we have to express is we have to express everything in terms of our generalized coordinates. So, express oh, my brain is always faster than, so express xb and omega prime b in our QJs. Okay, yeah, that's a very strange mixed notation, so maybe I'll just do a vector here too, right? So we have to express all the COM coordinates and all the body fixed angular speeds into terms of our generalized coordinates. By the way, note, still no angles, right? Interesting. Okay, Newton part. Because these, and why do I dissect so easily? Because this is really not connected to this. These are two disconnected things. Of course, the moment we express everything into generalized coordinates, it will be connected. But for now, it's disconnected. Okay, Newton part. How does that work? Well, we have to express all our body, COM coordinates of the body, as a function of our generalized coordinates. So we have these transformation functions, right? And of course, how do we find the speed? Well, we just differentiate x dot b is t b with respect to q times q dot, and then the accelerations which we need in the expression is again the tb comma q times q double dot plus all these convective terms. And now the index notation really works, because you have something like this, and we try to write that more in a more shorthand notation, tb q double dot plus, and then we say convective terms, and I use the word h here, hb. So these are convective terms, and the word convective comes, I think, from fluid dynamics or something like that. Okay, then the Euler part. How does that look? Well, for the Euler part, we have to express, for now, not the angles, because well, I see no angles in my equation, right? So if we go back to here, there are, go back to here, yeah. If we go back to this equation, there are no angles there. There's only torques, angular speeds, mass moment of inertia. I see no angles. Okay. Well, that's how it is. So I have to express my angular speed of each body in terms of my, general speeds. But it's probably also a function of the generalized coordinates, because how the bodies are orientated determines how body fixed angular speeds are, right? It depends also on the orientation of the body, so in this case on the generalized coordinates. So function of 2, but this is always linear in q dot, right? So if it's always linear in q dot, we can always write for the angular speeds, oh, it's a matrix times this q dot, so it's a matrix which I will call B for every body, and it's a function of the generalized coordinates times q dot. Okay. Then the speeds, well, we already have a speeds here, right? So, and you could say, of course, virtual speeds are, yeah, here likewise, virtual speeds are just the same mapping TB, comma Q, virtual speeds here. And likewise here, virtual angular velocities is again this same matrix BB, and I drop now this thing Q dot. Okay. Because why do I write that? Because here in the expression we need, of course, the virtual velocities and the virtual angular velocities. Okay, we're almost there, right? Then, oh yeah, I need angular accelerations, B, and that is, well, I keep the first part constant, so I get BBQ, Q double dot, plus, and then I get B, BB, yeah, with respect to Q, right? And then times Q dot, and again, so BB Q double dot plus, and I'm gonna make a shorthand term, and I had used G here, which is sort of confusing with gravity, but well, that's how it is. So again, these are convective terms. Convective terms. I think we now have our whole toolkit filled with all the stuff. So what we do is we then substitute this in the virtual power expressions, right, for the system, which is then the sum, of course, the virtual power of all the bodies. And then we take, yeah, all virtual generalized velocities, as long as they're not zero, and then we get equations of motion as many as there are q's, right? And that is the whole show. That's the whole show. And if we do that, then how does that end up? Well, okay, again, so then this virtual power expression becomes the sum over the bodies. Yeah, of course, the first part is the Newton part. So it has to do with the mass matrix of all the bodies. And remember, then we have this transformation matrix, the T. Oh, I zoomed. Huh. Okay, let's fix that. In all my enthusiasm, I zoomed. Okay, we have our virtual power expression, which is the sum over all the bodies of. Then, of course, I start with our stuff, which is times the acceleration. And what is that? Well, that's two parts again, right? That's the Newton part and the Euler part. So I can write the plus here. Notice that I use like a helicopter view now to derive all the things. I can do a linear way to start from the beginning of the equation and stitch my way, and that's of course the way it goes. But since this is education and we know already a lot, you can use the helicopter view and have first a general idea about the equation and then move down, right? So the general idea is we have mass times acceleration is forces. And so I know acceleration is forces. I already know forces because these are the applied generalized forces, right? Plus maybe some other terms. Convective terms and transformed terms of the bodies, which we'll see in a second. And this is, in our case, it's just m alpha, m beta, m gamma, right? Then the first part, the inertia. Well, remember from the TMT method, we have a mass matrix, and that's transformed by a transformation matrix, T T, and then T transpose B, Q, the Jacobian. That's the first part. Likewise, for the Euler equation, we have the same, only now it's the mass moment of inertia matrix for all the bodies, and they are transformed. Well, here the transformation is called B, right? So it's transformed B, B, and B, B transformed. So, and there's no, there is no comma Q involved here, because, of course, this is already, the B is already describing the mapping of the velocities, right? Okay. Yeah, go back to 100%. Okay. Then on the right hand equals generalized forces, generalized coordinates, generalized forces, plus, and then again we can write that in two parts. That's at the right hand side of the equation. So first let's take the Euler part. Then we have forces, and these are just applied forces, remember, and then we have to subtract from those applied forces the convective forces, convective acceleration times mass, so that was h, right? That's why I wanted to do a bit shorthand. And then this is all transformed like here, like this transformation. It's transformed here with this Jacobian. So that's the first part, and then of course the second part is the Euler part, and yeah, you can, well, this guy should be there. Inertia terms will be a bit more complex, but we have applied torques. It's all the same realm, so we get B transformed times, then we have the torques, and remember these are in the body oriented frame, body fixed frame, minus, yeah, and then we get inertia terms, and maybe I should do a curly bracket here, because these inertia terms are, of course, these convective terms are convective acceleration, right? And we call that G of B, very confusing. But note that we started our Euler equation with already a convective term. If you go way back to our Euler equation, did I ever write it down? Yeah, here. We already have a convective term, irrespective if we do coordinate transformation. We already have this stuff. So let's go there. Oops, 100%. Yeah, so now I have to do plus omega prime. It's in the prime, it's a cross product, and it's the omega b prime. So that was the angular momentum, sorry. I have to close the curly bracket, I have to close the round bracket, and I have to close the straight bracket. And all these closing brackets tells you that it's quite a nested thing. It's a sum of terms, which is also a sum, because this is sort of a summation thing too. And these are the equations of motion. Finally, if you do that, what do you get? Well, you just simply get a mass matrix times acceleration is forces, right? Force vector, sorry. Why do I put, yeah, bar there, of course. And that's it. That's the whole story, actually. And it took us less than half an hour. This is the way to derive your equation of motion for any multi-body dynamic system in terms of generalized coordinates. And of course, if there's closed loops, you can solve that by either cutting the loop or doing coordinate projection or any other. That's all in your toolkit. You can use all the tools from that toolkit. Now it looks as if you're done here, but there is a small snake here, of course, and that is, and now I have to go back to the top. Well, we are very experienced in writing this, right? expressing coordinates as a function of generalized coordinates. A bit new are we in the field of expressing, in this case, angular velocities in terms of our generalized velocities and our generalized coordinates. So I want to put some extra attention there how to do that. So, okay. So let's look at omegas versus q and q dot. That is now the topic, right? Again, we have to draw a picture. And so we have the disk, right? Here we have our inertial system here. X, Y, Z. On top of that we have this body 1 system with X, Y and Z remains the same. And yeah, let's give it directly a name. So there's alpha here, so there's here this angular speed, right? So you could say there is a vector here, omega alpha. And I'm not saying in which coordinate system. Then we have attached to that this one hinge, right? Let's get rid of the Y here. So this is the Y-axis. We have this one hinge here, and yeah, and then connected to that we have another hinge, and it's sort of nice, I think. So the coordinate was beta here, and then we have the other one here, and then finally we get our body here. And there's a coordinate system here, or triad, I should say, because the coordinate system has an origin, and for orientation, only the directions are important, so we call it triad. So, and this is called B2. But you need also some intermediate coordinate system here, right? And for Pete's sake, I will now write that. I will call that F or something like that. We need that in our derivation. So this was body 1, and this was body 2. Again, in this picture we can draw arrows in the sense of, oh yeah, this is an omega vector of beta, and this is like a omega vector of gamma, right? In our picture we can draw that as a vector with a clear direction, like it's along this direction. Since we defined all these triads, all these coordinate systems, we can follow the chain and know where everything is. And why do we do that? Because we need to express our angular speeds in terms of our goal here. Our goal here is to have our omega prime be expressed in our q's and our q dots. That is the goal. So let's start with body 1. Then we have this omega 1. And since we do it in our prime system, right, we do it in B1. And what is that? Well, yeah, I know already that this omega. Well, no, let's stop. Let's do an intermediate step. We're not going to express it yet in a frame. First, we write the vector equation. So omega of body 1 is, well, omega alpha, right? And for body 2, we can say the same easily. Omega of body 2 is, and that's simply the chain. It's this one, this rotation, and then we get this rotation and that. And it's just the chain of that rotation. So that is in our case. And why? Because it's a chain in itself. So that's omega alpha plus omega beta plus omega gamma. And still, I haven't used any coordinate system. Of course, in the end, I have to, because I have to determine in some coordinate system. So again, omega 1, I have to express in body 1. Well, that is, of course, very simple in our case. it's just the omega alpha, because although they're not the same, well, formally you should write the following, right? I know what the omega alpha is. I know the omega alpha in the inertial frame. Then it's a rotation about the z-axis, 0, 0, alpha dot, right? So I can write, oh yeah, that I know that guy, that is the omega in the n frame alpha. Oops. But I need it in the B frame, so I need a rotation matrix from n to B1. However, note that in our case, since it is a rotation about this z-axis, this doesn't really affect this one, because the z-axis will remain the same, right? So that's a deep thing. Meaning this rotation matrix, how does that look? The z-axis doesn't change, so whatever happens here doesn't matter. The outcome is always, again, 0, 0, alpha dot, right? So you could also say, well, if these two axes are aligned, I can either take the inertial frame coordinate or the body fixed coordinate. They are identical for along this axis. But that's just for formality, right? So you just, so you know. Actually, I have a different setting. So actually you could skip that. But for formality, I just write it there. Okay, that's body 1, that's easily done. So this is the expression for so omega 1 prime is, the B matrix in this case is super simple. So we wrote that is B1 times Q dot. And then the outcome should be this. So what is then this B matrix? Well, we can form the matrix, right? Then we get alpha dot, B dot, gamma dot. Now notice that the alpha is here, and then suddenly, bang, the alpha becomes there. So clearly, these angle things are no vectors. These are generalized coordinates, and these are time derivatives of generalized coordinates, right? So change in order. This is a vector, angular velocity vector. This is just Q dot, a vector. Has nothing to do with angular velocity or whatsoever, right? So this was angular velocity vector, this was omega vector. So there's a change in order. That's very important to note. Okay, what is then the B matrix? Well, the first entry should be 0, so that's 0, 0, 0. The second entry is also 0, 0, 0, 0, and the third entry is a alpha dot, so that's 1, 0, 0. That's our, so this is our B1. It's very simple. It turns out not to be a function of the generalized coordinates, but okay, that can be done because it's probably first in line. So omega 2. Well, omega 2 we have to express in body 2. And we know, of course, that's the sum of all these different omegas. It was omega alpha plus omega beta plus omega gamma, right? And now actually we need to look at the picture again. And how do I do that? I copy my picture maybe. That will be handy. Yeah, let's do that. Time-wise, yeah, I'm gonna use, like last week also, I'm gonna use 15 minutes to finish up this talk. And then we have a 5-minute break, and then we do the Q&A. Okay. So I say duplicate, and then I put that figure here. Yeah, and then we zoom out again to 100%. Where are you? Yeah. And of course, if we want to transform everything to our B2 system, to this system, and maybe we can draw a nice arrow here. So here we have our, yeah. Oh, yeah. Is it helpful? I don't know if it's helpful. You can draw an arrow here, omega 2. You can draw an arrow here and say that's omega 1. I don't know if that helps, but anyway. We have to express them in these body fixed frames. Now, the last one, the omega gamma, is already in the x direction, right? And of course you could say, oh, I need then the transformation from B2 to F, but that's rather simple. But still, let's write it. So I know this omega already in our B2 system, because this omega gamma in the B2 it's just a simple rotation about the x-axis with minus gamma dot. And minus because, well, plus is in that direction. Yeah, I just took the minus x direction, whatever, it doesn't matter. I could also have drawn the hinge the other way around, but then this hinge would obscure, make this hinge visible, so that's why I did it to the back. But it's just a sign. Okay, minus gamma dot, that's okay. And I know it in the B2 frame, so I say, okay, I know that in the B2, and then I need a transformation to B2. So there's nothing. I need no transformation here, so that's just the identity. Then the omega beta. I know that one in which frame? Well, like in the F frame, right? In that intermediate frame. So that's this guy. And I know that's about the y-axis, right? So that's 0, beta dot 0. So I know this guy. And then I need a transformation matrix from F to B2. So I could say here identity, so yeah, maybe we shift it. No, it says no transformation. And then maybe shift this a little bit. Unclear, so this is B1, right? Oh yeah, let's delete that. From F to B2, and well, that's just a transformation with angles, we will get to that in a second. And then the last one, omega alpha, I know that one in B1 or in N, doesn't matter, so let's say B1. So I know my omega alpha, I know that in B1, and that was a rotation about the z-axis, right? 0, 0, alpha dot. So I write B1 here, and then I read a rotation matrix from body 1 to body 2. Okay, almost there, because we have defined all the singletons, so we have defined these guys, right? We know what they are. And now the only thing is we have to define, well, here's nothing, we have to define these two rotation matrices. So we can again look at this figure by doing that. And the first one we're going to derive is our rotation matrix from F to B2. And of course that is a function of gamma only, right? But notice it's not from B2 to F, but it's from F to B2. So it's not the one we usually do from the local to the inertial, but now it's the other way around. But that doesn't matter. We can just write that down. That one is simply, well, what doesn't change, that's the easiest part. The y-axis doesn't change, right? The x-axis doesn't change, sorry. So 1, 0, 0, 0, 0. And then we have cosine and sine of gamma. And somewhere there's a minus sign. If it would be a regular transformation, the minus sign would be up here. But now it's a transpose, so the minus sign should be here. And maybe I make an error, just check it. Yeah. Okay, so that is covered now. So this guy is covered. Now we need to know this one. So we have to go from this body to this body, right? Because this angular speed has to go to this body. So from this one to this. And then we see, oh, I can go from B2 to F, and I can go from F to B1. So let's write that out. So if we need the rotation matrix from B1 to B2, that is just the chain of B2 to F to what am I doing? Oh, I have to do it. Yeah. Fry my brain. I have to do it the other way around, of course. I have to do. Yeah, I know that I only have to go from. I have to go from B1 to B2, right? Let's check that again. Backwards from B1 to B2. Backwards, backwards, backwards. B1 to B2 is, well, the outcome should be B2. Intermediate is the F, and then the rotation matrix from F, B1. What did I do wrong? Oh yeah, that's good. B2F, yeah. Well, B2F we already have, right? That's this guy. Okay, so then the only thing we have to define is this guy. Rotation matrix from B1 to F is, and that's again a rotation matrix which is a function of, so from B1 to F. So what is the difference? Well, the difference is, oh man, this should be beta, of course, huh? Oh, yeah. Okay. Okay. Anyway, so here we get the beta, right? And then what changes with the beta? What changes with beta is that's about the y-axis, so nothing changes at the y-axis, so 0, 1, 0, 0, 0, right? Nice cross. And then again the cosines and the sines of beta, and the only thing we have to put into place is a minus sign, and yeah, the regular minus sign would be here at the lower corner, so my guess is that the minus sign should be here, but check it, huh? Check it, because I tend to make errors. And then of course it's a multiplication of those two. And then you can easily write out what the thing is, and then finally we get our expression for omega of 2 with the prime is B2, and B2 is now clearly a function of these angles, but it should be of Q. But notice, by the way, that looking at these matrices, alpha doesn't come into play. So the only thing which we will see here, it is a function of this alpha, beta and gamma, but of this beta and gamma. But for generality, I just write alpha, beta, gamma, function of that one, times, and then we say alpha dot, beta dot, gamma dot, right? Yeah, that's a dangerous bend to try and write that out. So that's nice homework for you to do, actually, to write that out and check it. Of course, we already know some of the parts, right? We already know that the gamma dot doesn't change for B2, and the gamma dot is always about the what was it, the minus x-axis, so there should be a -1 for the gamma dot. So there is probably a -1 here, right? -1, because this is like omega x, omega y, omega z expressed in B2. Wow. And the rest is just for you to do. Well, final word, if you for coding, if you code this in MATLAB or Python, then it's a two-stage rocket. So this is stage 1, and this is stage 2, and this is you. Stage 1 and stage 2. Stage 1 is symbolic. Stage 2 is numeric. So what do you do to get to the moon, Apollo 11 or whatever? You need a big rocket, which goes upside down, but you need a big rocket with a large first stage, and in this case the large first stage is this booster thing, and then a smaller second stage is this numerical thing. Why? Well, because in deriving the equations of motion, you use the symbolic part to do all the matrices and all the differentiation. But to calculate numbers, you just use these atoms, evaluate the atoms numerically, and then express them. Because you do not want, if you do everything symbolic, then the result is horrible. Horrible. You get explosion of terms. And so most of you have seen that also in their homework. So as an example again, if you have A plus B, and you do that symbolically, then if you do symbolically A plus B, you get A plus B, and then you do squared. Then squared, what do you get? You get A times A plus A times B plus B times A plus B times B, right? So the final expression for this will be this. And how many operations are there? There are like 4 multiplications. Oh, let's write that in words. There are like 4 multiplications plus 4 additions, right? Okay, now say you do it numerically. Okay, then you have A is 2, so you just assign a number, and then B is 4. And then you do A plus B is 2 plus 4. And the answer is of course 6. Now how many operations was that? That is 1, that's 2 assignments. Assignments. You have to do assignments here anyway, by the way, so forget that. If you want to, and then, well, and then of course, sorry, squared. Yeah, that is very unprofessional. Very unprofessional. Okay, let's do it again. So you have a plus b, and that is 6, right? And then you have a plus b squared, and that is 6 squared, and that is 6 times 6, and that's 36. Anyway, the number of operations, forget the assignments, you have to do that here too. And the only thing which is happening here is, of course, we have one addition plus one multiplication. And compare that between the two, right? So that clearly indicates that, and this is only a plus b squared. I mean, remember in your case you have cosine, sine, square, differential, matrices, a lot of additions, multiplications. So if you drag on this whole numerical calculation to do and to do like, and we have to go all the way back here to do this stuff, if you do that all symbolically, you get code which is takes forever. However, if you do every single part symbolically and then in a script write them and then evaluate them numerically, and you don't write them in a script, you make functions out of those, right? As I've shown in the homework, then you get code which is very manageable. Oh, that's exactly homework assignment number, what is it, 11? Yeah. Yeah, so the two-stage rocket is important, otherwise you will never get to the moon. Who wants to go to the moon? I don't know. Do not forget to register for the exam. The exam. Because, and the exam is, it's digital and it's online, right? And it's, yeah, sort of proctored. In the sense that you have to hand in all kind of things. I cannot look over your shoulder, unfortunately, but we have found a way to do sort of proctoring that you can still relax your work without being interfered by people looking over your shoulder or checking while you're doing your work, but at the end we can then check if it's your work or work by others. Okay. Oh, we ran out of time. Oh, I talked too much. Okay, let's take a 5-minute break and then we go to the Q&A. So Q&A in Zoom at, yeah. Oh man, time is running when you're having fun. 9:55. Okay. Stop the show. Thank you. It was fun this year. Difficult, but in the end it sort of worked out for me. Hopefully for you too.